All right, in this lecture we're going to finish the section 4.5 material on the dimension of a vector space. And the second half of our section deals with subspaces of a finite dimensional space. So we'll start this section, or this lecture, by presenting a couple of theorems. The first of which is considered as a counterpart to the spanning set theorem. So recall that the spanning set theorem said if we have a vector space or a subspace of a vector space, which is spanned by a finite number of vectors, and one of those vectors can be written as a linear combination of the others, then we can remove that vector from our spanning set, and the resulting set will still span our vector space or our subspace. So the following theorem, Theorem 4.11 from your textbook, says if we have a subspace H of a finite dimensional vector space V, then any linearly independent set in H can be expanded, if necessary, to form a basis for H. So if we have a linearly independent set within a subspace of a finite dimensional vector space, then we can expand it in order to form a basis for that subset if needed, if it's not already a basis. Moreover, H is finite dimensional, and the dimension of H is less than or equal to the dimension of V, the subspace the vector space which it is a subspace of. So let's consider the proof of this theorem. Let's see if we can establish this result. So we'll start by considering the simplest possible subspace, that is the zero subspace. So if H is equal to the zero subspace, then the dimension of H is 0, which is certainly less than the dimension of the vector space V, or less than or equal to the dimension of V, which this is a subspace of. Otherwise, so if we're considering a non-zero subspace, let's consider a set S of vectors u1 through uk, which will be a linearly independent set in the subspace H. So if this set S spans the subspace H, then S is a basis for H by definition. So if we have a set S, which is linearly independent in the subspace H, and it spans H, then by definition S is a basis, a linearly independent spanning set for our subspace. Otherwise, that is, if S does not span H, that means there is a vector, let's call it U sub k plus 1 in H, that is not in the span of the vectors u1 through uk. So if that set S does not span the subspace H, that means there exists some vector in H which is not within that span. So then, if we consider the set S, which was the vectors u1 through uk, but we expand by adding this vector uk plus 1, which was not already in that spanning set of the set S, this set is linearly independent since no vector in this set is a linear combination of the preceding vectors. By Theorem 4.4. So by adding that additional vector uk plus 1, we still have a linearly independent set of vectors because uk plus 1 was not a linear combination of the preceding vectors, and the set S was already linearly independent in the set H. All right. So we can add this additional vector to our set S, and as long as this new set does not span H, we could keep adding additional vectors. So let's say as long as the new set does not span our subspace H, we can continue the expansion of our set S to a larger linearly independent set in our subspace H. But by applying Theorem 4.9, the number of vectors in this linearly independent expansion of our set S can never be larger or can never exceed the dimension of the vector space V. So at some point, this expansion that we're considering must span our subspace H, and will therefore be a basis of H since our set was linearly independent. So we can say eventually the expansion of our set S will span the subspace H and will be a basis of H. And the dimension of this subspace H must be less than or equal to the dimension of V as guaranteed by Theorem 4.9. All right. So we've established this result. If we have a subspace of a finite dimensional vector space, then any linearly independent set within that subspace could be expanded to find a basis. So this gives us a way to create a basis for a subspace. Or H, or not or, but also H is finite dimensional. So any subspace of a finite dimensional space is finite dimensional, and its dimension must be less than or equal to that of the space of which it is a subset. All right. Now the following theorem has some very nice applications in differential equations and some select other fields. So this theorem will say if the dimension of a vector space or a subspace is known, then the search for a basis for that vector space or subspace can be simplified by the result of this theorem. So in particular, this next theorem will say if we have a set which has the right number of elements, then we only have to show that either that set is linearly independent or that that set spans our vector space. So in particular, this theorem will, or if we're interested in finding a basis for a vector space or a subspace, we would have to find a set of vectors which is a spanning set for that space, and it's linearly independent. Now, this next theorem will say as long as we know the dimension of a vector space or a subspace, that is, we know the number of vectors that are supposed to be within a basis, we only have to show that a set with that number of vectors is linearly independent or that it is a spanning set of our vector space. We don't have to show both. However, we do have to know the dimension of that vector space. So this result is known as the basis theorem, and it says if we have a vector space V, which is p-dimensional, where p is greater than or equal to 1, so it is finite dimensional where the dimension is at least 1, then any linearly independent set consisting of exactly p elements of our vector space is a basis for that space. So that is, if we have a set of p vectors in a vector space of dimension p, and those vectors are linearly independent, then that set must be a basis. And similarly, any set consisting of exactly p elements from the vector space V which spans V is a basis for V. So the basis theorem says if we have the correct number of vectors for a space of dimension p that's known, we only need to show that that set is linearly independent or that it spans our vector space in order to show that it forms a basis. So let's see if we can establish this result. So by making use of the previous theorem, that is theorem 4.11, a linearly independent set let's call it S, of p elements, that is p vectors, can be extended to a basis for our vector space V. So we saw in that last theorem, if we have a linearly independent subset consisting of p elements from a vector space, we can extend that linearly independent set if needed to be a basis for our vector space. But that basis must contain exactly p elements since the dimension of our vector space is equal to p. So this set S must already be a basis for V, because we cannot expand it any further, since the dimension of our vector space is P, and the dimension of some subspace must not be any larger, and this set S already contains P elements. It must already be a subspace for our vector space. So we've shown if we have a set of P linearly independent vectors in a vector space of dimension P, then that must form a basis. Now, the second part of this theorem says if we have a set of p vectors from a vector space of dimension p, which span that vector space, then that must be a basis. So let's consider the proof for that part of our theorem. Let's suppose that we have a set S, which has p elements, or p vectors, and spans the vector space V. Now, in the hypotheses of this theorem, we said that V has dimension at least 1. So since V is not equal to the 0 subspace, the spanning set theorem implies that a subset, let's call it S prime of our set S, is a basis for the vector space V. However, since the dimension of our vector space is equal to P, which is the number of elements in the set S, that means that the subset S prime must contain P vectors. Therefore, the subset S prime is equal to the set S, since they have the same number of vectors. So we've established this basis theorem. All right. Now in the next part of this section, we'll talk about determining the dimension of the null space of a matrix or the column space of a matrix. So let's recall some results that we've seen in previous sections. Now, if we're considering the pivot columns of a matrix A, we know that those pivot columns form a basis for the column space. We saw that in section 4.2. So we know that the dimension of the column space of a matrix A as soon as we know the pivot columns. So since the pivot columns form a basis for the column space, the number of pivot columns is equal to the dimension for the column space of A. Now, the dimension for the null space of a matrix may seem like it would require more work, because in order to find a basis for the null space of A, we have to solve a homogeneous system of linear equations by performing row reduction on a matrix A. So it certainly seems like it should take more time than finding a basis for the column space. However, there is a shortcut. So if we consider a matrix A, which is an m by n matrix, and we consider the equation AX equals to 0, so that X is an element of the null space of A, and this equation has k free variables, or our solution, X, has k free variables. We know from our section 4.2 material that the method that we would use to find the spanning set for the null space of A will produce k linearly independent vectors, say u1 through uk, where we have one vector for each free variable. So the set u1 through uk is therefore a basis for the null space of A, since these vectors are linearly independent, and the number of free variables determines the size of the basis. So in summary, the dimension of the null space of a matrix A is the number of free variables in the equation AX is equal to 0, and the dimension of the column space of A is the number of pivot columns in A. All right. So Having said that, let's consider some examples. So in this first example, we are asked to find the dimensions for the null space of the given matrix and the column space. So let's start with our column space. We can see that this matrix A is already in row echelon form, so we can determine the number of pivot columns. So looking at the form of this matrix, we see that we have, counting our pivot columns, 1, 2, 3 pivot columns. So the number of pivot columns is the dimension of our column space. So here, the dimension of the column space of A is equal to 3, and the dimension of the null space of A is equal to the number of free variables that we would have in the equation AX equal to 0. Now recall, if we have a matrix which is already expressed in row echelon form, the free variables correspond to the columns which do not have pivots. So in this example, we have 1, 2, 3 columns without pivots. So the dimension of the null space would also be 3 here. So let's look at our next example. Same sort of problem. We are asked to find the dimensions for the null space and the column space for the following matrix A, which is already in row echelon form. And we can see that it has 2 pivot columns. Therefore, the dimension of the column space of this matrix A is equal to the number of pivot columns, which was 2, and the dimension for the null space of this matrix A is equal to the number of free variables for the system AX equals to 0, and we can see from our matrix that there is 1 free variable, 1 non-pivot column. Therefore, the dimension of the null space is 1. Okay. So let's consider a similar example, just maybe worded in a different way. We're asked to find the dimension of the subspace H of R2, which is spanned by the following vectors. So here we have a collection of 3 vectors in R2. Therefore, since we have more vectors than the length of those vectors, we know that they are linearly dependent. So one of these vectors can be dismissed from the span. So the question is, how many vectors can we exclude so that R2 would be a spanning set for this set of vectors? So we know we can discard at least 1. However, in order to span R2, which has dimension 2, we need at least 2 vectors. So intuitively, we could say, well, the dimension should be 2 here. So let's see if we can justify this. Another way that we could approach this problem is to think about H, which is the span of these 3 vectors. Let's maybe give them names, v1, v2, and v3. We can think about this space as the column space of a matrix A, where the matrix A is the matrix whose columns are these vectors. So here we just have a 2 by 2 matrix, 2, -5, -4, 10, and -3, 6. So in order to find the dimension of this space, we're looking for the dimension of the column space of a matrix A, shown here, which we've already said is the number of pivot columns for this matrix. So let's perform row reduction on this matrix to see if we could simplify a little bit. So let's see what we could do here. In order to simplify, I've got a leading entry of 2 in my first row. I want to use that to eliminate the -5 in my second row. I see that I have an entry of -3 in my first row, third column, which I could use to kill off the 6 appearing in the second row, third column, by taking row 2 plus 2 times row 1, which would make my first row 2, -4, -3, and my second row then becomes 4 minus 5 is -1, -8 plus 10 would be +2, and -6 plus 6 is 0. So simplifying a bit further, I could use the leading -1 in my second row to eliminate the 2 from my first row. Or I could add the second row to the first to get a leading 1 in this top left entry. That is, take row 1 plus row 2. So I would have 1, -2, -3. And my second row will remain the same, -1, 2, 0. So adding my first row to the second row, that is row 2 plus row 1, I have 1, -2, -3, and my second row becomes 0, 0, -3. So at this point we have our matrix in row echelon form. And we can see that there are 2 pivot columns, which would be the dimension of the column space, which is the same as H here. So the dimension of this set H is the same as the dimension of the column space of this matrix A, which we've established has 2 pivot columns. So here our dimension of this subspace is 2. The same that we would expect considering a more intuitive approach where we have a set of 3 vectors spanning R2. So in our next example, we have a similar problem where we are asked to find the dimension of the subspace, which is being spanned by the following vectors. So we could name these vectors maybe V1 through V4. And the space that we're considering, H, is the span of this set of vectors, V1 through V4, which could be thought of as the column space of a matrix A, where A is the matrix which has these vectors as its columns. 1, -2, 0, -3, 4, 1, -8, 6, 5, and -3, 0, 7. So by performing row reduction on this matrix, we could determine the number of pivot columns and therefore the dimension of this column space and the dimension of H. So let's see what we could do to reduce our matrix here. So I already have a 1 as the leading entry in my first row. I'm going to use that to eliminate the -2 that appears as the lead entry in my second row by taking row 2 plus twice row 1, which will make my second row 0, -6 plus 4 is -2, -16 plus 6 is -10, and negative 6 plus 0 is negative 6. My third row I'm going to leave alone for now. And in order to save myself a little bit of work, I'm going to use the leading 1 in my third row to kill off the negative 3 in the first row by taking row 1 plus 3 times row 3, which will make my first row 1, 0, 15 minus 8 is 7, 21 minus 3 would be 18. All right. So now, my leading entry in the first row is 1. I have zeros below it. In my second column, I have a leading 1 in the third row, which I could use to eliminate the negative 2 in the row above it. Or I see I could divide my second row through by negative 2. So I'm going to use that approach. Let me take negative 1/2 of my second row. So my first row is 1, 0, 7, 18. My second row becomes 0, 1, 5, 3. And my last row is 0, 1, 5, 7. So now I have the leading 1 in my first row with zeros below it, a leading 1 in my second row with a 0 above it, and I just need to eliminate the 1 as the leading entry in my third row, which I can do by taking row 3 minus row 2. So I have 1, 0, 7, 18, 0, 1, 5, 3, and 0, 0, 0, 4. So now, the leading entry in my first two rows is a 1 with zeros above and below in that column. And the leading entry for my third row is a 4, which I want to be a 1. So I'm going to take 1/4 of row 3, which makes my third row 0, 0, 0, 1. My first two rows I'm going to leave alone. All right. So now, using the leading 1 in that third row, I can kill off the 3 and 18 that appear above it by taking row 1 minus 18 row 3, or row 2 minus 3 times row 3, which gives me the matrix 1, 0, 7, 0, 0, 1, 5, 0, and 0, 0, 0, 1. So the dimension of the space that we're interested in, which would be the dimension of the column space of this matrix, is 3. We see that we have 3 pivot columns. So here the dimension of H, which is the dimension of the column space of this matrix A, is 3. All right. So to finish out this section, we'll consider an application of the coordinate mapping that we had seen in the previous section in determining the dimension of a subspace of polynomial space. So in this example, we will consider the following. We have the first 4 Laguerre polynomials are 1, 1 minus t, 2 minus 4t plus t squared, and 6 minus 18t plus 9t squared minus t cubed. And we are asked to, in part A, show that these polynomials form a basis of P3. So polynomial space is a little bit unfamiliar. It's a little bit trickier to work with than vectors and Rn, but we know that the space of polynomials, P3, is isomorphic to R4 using a coordinate mapping. So if we were to convert these vectors, these four polynomials in P3, to their corresponding vectors in R4, and we can show that those vectors form a basis for R4, then these vectors must form a basis for P3 by use of this isomorphism. So let's consider the following. Here we have mentioned that the dimension of P3, the set of polynomials of a degree 3 or less, is equal to 4, as we saw in the earlier part of our section. And if we consider the coordinate vectors, for these polynomials, we would have the following. So the coordinate vector for the first polynomial with respect to the standard basis b, so here let's maybe write out what our standard basis is. So for these polynomials, let's say relative to the standard basis b, which would be the set 1, t to the first, t squared, t cubed. These vectors are P1, which is equal to 1, and then there was 0t, 0t squared, and 0t cubed. The coordinate vector for the second polynomial with respect to our basis b, well, we had 1 minus 1t, 0t squared, and 0t cubed. The coordinate vector for P3 would be 2, negative 4, 1, 0, and the coordinate vector for P4 with respect or relative to our basis b is 6, negative 18, 9, negative 1. So we want to know whether these four vectors in R4 form a linearly independent set or a basis for R4. So to determine whether these vectors form a basis for R4, we could consider a matrix A, which has these vectors as its columns. Recall, to show that this is a basis, we need to show that these vectors are linearly independent and form a spanning set of R4. So an easy way to accomplish that is by to consider the following matrix, whose columns are these vectors: 1, 0, 0, 0, 1, negative 1, 0, 0, 2, negative 4, 1, 0, and 6, negative 18, 9, negative 1. Now this is a square matrix, that is a 4 by 4 matrix. So to show that the columns are linearly independent and span all of R4, we could use the invertible matrix theorem. That is, if this matrix is invertible, this set of column vectors is linearly independent and spans all of R4. Therefore, it forms a basis of R4, and our polynomials would form a basis of P3. So, to show that this matrix is invertible, we could consider its determinant. Now, this matrix A is an upper triangular matrix. So recall, the determinant is the product of the diagonal entries, which would be 1. And since our determinant is non-zero, that means that A is invertible. So, by the invertible matrix theorem, the columns of A are linearly independent. So here we have a set of linearly independent vectors. The number of vectors that we have, 1, 2, 3, 4, is equal to the dimension of the vector space. So theorem 4.12 says, as soon as we've established that these vectors are linearly independent, we know that they form a basis. So here we can say by theorem 4.12, these vectors form a basis for P3. All right. So again, this example illustrating that if we're working with a somewhat unfamiliar vector space like a space of polynomials, we can use the coordinate mapping to think about those polynomials as vectors in Rn, in this case R4, and once we've shown that those vectors form a basis, the corresponding vectors in P3 must also form a basis. So in our last part of this example, part B, we're told to let B be the basis of P2, consisting of the first three Laguerre polynomials, and let P of t equal the following polynomial, and we're supposed to find the coordinate vector of P relative to this basis. So this is really just a review of what we've already seen in our previous section, where we're finding the coordinate vector relative to some basis. So the basis coordinates for this polynomial P must satisfy the following equation. If we take the first coordinate, C1, times the first of our three Laguerre polynomials, which was 1, plus C2 times the second polynomial, which was 1 minus t, plus C3 times the third of those polynomials, 2 negative 4t plus t squared, we should get the polynomial P, which was 7 minus 8t plus 3t squared. So expanding and grouping like terms, we have a constant coefficient of C1 plus C2 plus 2 times C3. We have a t coefficient of negative C2 minus 4 C3. And we have a t squared coefficient of C3. This has to equal 7 minus 8t plus 3t squared. So equating the coefficients, we have the following system of equations. C1 plus C2 plus 2C3 has to equal the constant coefficient of our polynomials 7. Negative C2 minus 4 times C3 has to equal negative 8. And our t squared coefficient C3 has to be 3. So let's consider this system of equations as an augmented matrix. We would have 1, 1, 2, 7, 0, negative 1, negative 4, negative 8, and 0, 0, 1, 3. So performing row reduction, we could take row 1 and add row 2 to it, which gives us 1, 0, negative 2, negative 1. I could take the negative of row 2, which would give me 0, 1, 4, 8, and my last row is 0, 0, 1, 3. So now I could use my third row to simplify my first two rows by taking row 1 plus twice row 3, or row 2 minus 4 times row 3. So my first row becomes 1, 0, 0, 5. Second row is 0, 1, 0, negative 4. And my last row is 0, 0, 1, 3. So these are the coefficients. C1 is 5, C2 is negative 4, and C3 is 3. Therefore, the coordinate vector of this polynomial p, relative to the basis described, is the vector 5, negative 4, 3.